Hi again, everybody. This is Trig Lesson 4 for Pre-Calculus 11. So I'm going to put specifically that this is trig. It's called angles in standard position. And I will call mine answer key. So far in trig, we have done the Pythagorean theorem. We have looked at SOHCAHTOA and how to apply SOHCAHTOA, and now we're into extending that a little bit further to angles in standard position. And angles in standard position are drawn on the Cartesian plane like so. The Cartesian plane is just the xy axis. You know how this is the y-axis and this is the x-axis. That's what the Cartesian plane is. Excuse me. Okay, and so an example of an angle on the Cartesian plane would look like this. The angle always starts from the positive x-axis. This is what we call the initial arm. Okay, and then we sort of go around in a circle, either clockwise or counterclockwise. The positive angles go in a counterclockwise fashion like this. That's just the convention. And so an example of an angle in this Cartesian plane, let's say we put a point out here. XY, and then the angle between the initial arm and this other arm, we give it a Greek letter named theta, for example. Okay, and this other arm here has a special name as well. It's called the terminal arm. Okay, and as mentioned, because you could sort of draw a bit of a circle here as the angle goes around in a circle, you'll notice that from the center of the circle to the edge, we usually call that the radius, and so this length is often shown with the letter R. Okay, and then we can erase the circle just so we don't have too much extra stuff on here. Okay, and so these are some of the conventions for angles in standard position. Okay, and you may also notice that in the Cartesian plane there are sort of four rectangles, four sections. Those are called quadrants, and they are labeled like so. This is quadrant 1, which we use Roman numerals for. This is quadrant 2, goes counterclockwise. This is quadrant 3, and this is quadrant 4. Okay, so I'm saying quadrants. Quad 1, quad 2, quad 3, and quad 4. Okay, and so that brings us to something called reference angles. For each angle in standard position, there is a corresponding acute angle. An acute angle is a small angle between 0 degrees and 90 degrees. So there is a corresponding acute angle called the reference angle. The reference angle is always between the terminal arm and the closest part of the x-axis. I'll show you what that means in a minute. The reference angle is always positive and measures between 0 and 90 degrees. Okay? The following shows the reference angle, theta subscript r, that stands for reference angle, illustrated for angles theta in standard position. Okay? So let's say we have an angle in the first quadrant called theta. The reference angle is always between the terminal arm and the closest part of the x-axis. So remember, the terminal arm in this case is that one there, right? It's not the one that's first starting on the x-axis. That's the initial arm. So the terminal arm is the one I've indicated there. And the angle that's between the terminal arm and the closest part of the x-axis is actually the same angle in that case right there. It wouldn't be this one over here because the x-axis over here is further away from the terminal arm. Okay, so in the first quadrant, what we end up getting is that if you draw out an angle theta in standard position, that theta is actually equal to the reference angle. Okay, so the reference angle is equal to the angle itself in that case. If we draw an angle in standard position in the second quadrant like this, here's angle theta from the initial arm to the terminal arm. This time, guys, the reference angle, remember it says the reference angle is always between the terminal arm and the closest part of the x-axis. So that means that the reference angle is here this time. That is theta reference. Okay, because it's from the terminal arm to the closer piece of the x-axis. And so in this case, how would we get the reference angle? Here's what you would have to do. Notice that it would be 180 degrees from the initial arm to the other piece of the x-axis. And then we've got from the initial arm to the terminal arm, that's angle theta. So to get the reference angle, you have to go 180 degrees minus theta. All right, how about quadrant 3? Let's say we have an angle here. So this whole thing is theta from the initial arm to the terminal arm. The reference angle is always from the terminal arm to the closer piece of the x-axis. So it wouldn't be over here, it would be this way. Oops. Okay, so this angle is theta reference. And what is theta reference equal to? What it would be is the full angle theta all the way around to there minus 180 degrees this time. Because if we subtracted off that piece right there, we would be left with the reference angle. And finally, if we have an angle in standard position in the fourth quadrant like this all the way around, we call that theta. The reference angle is between the terminal arm and the closer part of the x-axis, so that's theta reference. And then we need to come up with an expression for theta reference. The reference angle is equal to, how would I get that missing piece right there? Well, all the way around the circle is 360 degrees, and if I subtracted off angle theta, it would leave me that small little reference angle remaining. Okay, so let's do an example. The angles in standard position with a reference angle of 20 degrees are shown here. In the first quadrant, if we have a reference angle of 20 degrees, that would be right there. Okay, so we have the reference angle equals 20 degrees, the angle in standard position, 20 degrees. Theta reference equals the theta itself. They're the same. In quadrant 2, if we have a reference angle of 20 degrees, the reference angle is here, so the 20 degrees would be here. And so then angle theta would be like that. All right, and notice that those two angles together form a straight line. So this would have to be 160 degrees, right? You would go 180 minus the 20 degrees using that formula there. So theta reference is equal to 20 degrees. Theta is 160 degrees. Okay, how about a reference angle of 20 degrees in the third quadrant? This is where our 20 degrees would be. The whole big angle would be like that. So you can see that it's 180 plus 20. So that's going to be 200 degrees. Okay, so theta reference is equal to the 200 degrees minus 180, which is 20 degrees, and theta is 200 degrees. And in quadrant 4, if I draw a reference angle of 20 degrees, then what is this angle theta? Well, it's 360 all the way around the circle, so we would have to go 360 minus that 20 to get 340 degrees. Okay, so theta reference using this formula up here is 360 minus the 340, which is where we get the 20 degrees from, and theta is 340 degrees. Okay, so that brings us to some special right triangles. There are actually two special right triangles that look like this. There's one that comes from a 1 by 1 square. Here's where our 90 degrees is. And just imagine if this side was 1 unit in length and this side was as well. By Pythagoras, you can show that the diagonal here, the hypotenuse, ends up being the square root of 2 in exact form. And if this is 90 degrees, these angles end up being 45 degrees. Okay, so it's called the 1, 1, root 2 triangle, or 45, 45, 90 if you want to talk about the angles. And the other special triangle has measurements like this. This is 1 unit, this is 2, and if you do Pythagoras, you can show that this is root 3 over here. And the angles are 30 degrees, 60 degrees, and of course the box there means that that last angle is 90 degrees. Okay, and of course across from the 90 degrees, this is the hypotenuse, and over here this is the hypotenuse. Okay. And so using these triangles, we can determine the exact values of the trig ratios, sine, cos, and tan, for the angles 30 degrees, 45 degrees, and 60 degrees. Okay, and so we can do that using SOHCAHTOA. Right, trig ratios come from SOHCAHTOA. And let's start off with the 30-degree angle. So we'll do sine of 30 degrees, cos of 30 degrees, and tan of 30 degrees. Now sine of 30 degrees, remember sine is opposite over hypotenuse, so we would have opposite, and the hypotenuse is across from there. So the opposite is 1, the hypotenuse is 2. So sine 30 is 1/2. Cos 30, I'm looking at the 30-degree angle over here. Cos is adjacent over hypotenuse, so it's adjacent over hypotenuse as an exact expression, root 3 over 2. And tan of 30 degrees, tan is opposite over adjacent. There's opposite, there's adjacent, 1 over root 3. Okay, and now we will look at sine of 45 degrees, cos of 45 degrees, and tan of 45 degrees. So we need to be in this triangle on the left, and you can use either 45-degree angle, right? It doesn't matter which one you use, you'll get the same ratios. Okay, so let's use this one. Sine is opposite over hypotenuse, so that's 1 over root 2. Cos is adjacent over hypotenuse, so that's 1 over root 2 as well. So sine 45 equals cos 45. And look at what tan 45 is. Tan 45, tan is opposite over adjacent, so tan 45 is 1 over 1, which is 1. And now we will look at sine of 60 degrees, cos of 60 degrees, and tan of 60 degrees. So we're going to have to go back into the 30, 60, 90 triangle. Okay, so we're using the 60-degree angle. Sine is opposite over hypotenuse, so root 3 over 2. Cos is adjacent over hypotenuse, so cos 60 is 1/2, 1 over 2. And tan of 60 degrees, tan is opposite over adjacent. There's opposite, there's adjacent. Root 3 over 1, which we could just write as root 3. Okay. All right, so these are some exact values for trig ratios for the angles 30, 45 and 60 degrees. All right, let's check out example 1. It says, sketch each angle in standard position. State the quadrant in which the terminal arm lies. Okay, so we always start on the positive x-axis, and positive angles go in a counterclockwise direction. And you know how, like, all the way up to the positive y-axis, that would be 90 degrees. So 36 degrees would be somewhere in here. You don't have to have it exact, it just has to make sense. That would be about 36 degrees. Actually, I've made mine probably a little bit bigger than it should be, but as long as it's reasonable. Okay, so sketch each angle in standard position. State the quadrant in which the terminal arm lies. Remember, the terminal arm is that one. Okay, and so hopefully you can see that that's in quadrant 1, because the quadrants go 1, 2, 3, and 4. Okay, so this one is in quad 1. All right, how about letter B here, 210 degrees. Start with the initial arm right on the positive x-axis. That's 90 degrees. That would be 180. And to the next line, 180 plus 90 is 270. So 210 should be somewhere in here. Okay, there's 210 degrees. And then you can see that the terminal arm is in quad 3. Okay, and 315 degrees. There's our initial arm. There's 90 degrees, 180, 270, all the way around is 360, so 315 would be somewhere in here. There's 315 degrees. Okay, and you can see that that is in quadrant 4. Alright, example 2 says, determine the reference angle, theta reference, for each angle theta. Sketch theta in standard position and label the reference angle theta r. Okay, so this is theta, and we want the reference angle for that. So 130 degrees, there's the positive x-axis. Up to there is 90 degrees. To the next x-axis would be 180, so 130 would be somewhere in here. So here's theta equals 130 degrees. Okay, and we know all the way to this line we'll do a full 180, right? Because it's half a circle. So we would go 180 minus 130. This is going to be 50 degrees, and that is theta reference because it's between the terminal arm and the closer piece of the x-axis. Okay, so I think that's all we need to do for that one. And for 300 degrees, initial arm, there's 90, 180, 270, all the way around is 360, so 300 would be like that. .300 degrees to the terminal arm, and all the way around the circle is 360, so this should be the remaining 60 degrees, right? and that's between the terminal arm and the closer piece of the x-axis, so that is the reference angle. Alright, and finally example 3, determine the angle in standard position when an angle of 40 degrees is reflected A in the y-axis. So there's the y-axis, there's the x-axis, and we are starting off with an angle of 40 degrees. So imagine we have an angle of 40 degrees here, and it wants us to determine the angle in standard position when this angle of 40 degrees is reflected in the y-axis. Okay, so reflected in the y-axis means imagine taking that terminal arm and reflecting it over the y-axis this way. Okay, that would take that terminal arm and it would reflect it over the y-axis like that, and have the 40 degrees here. Okay, and if we do that, it creates this angle in standard position here, which is what they want us to find. So the angle in standard position when the 40-degree angle is reflected in the y-axis, if that's 40, we know from the positive x-axis all the way to the negative x-axis is 180 degrees. This guy would be 140. All right, let's try part B. So imagine the 40-degree angle is reflected in the x-axis. Here's the y-axis, here's the x-axis. Initial arm, terminal arm. Okay, so imagine there's our 40-degree angle. If we reflect that angle about the x-axis, so reflecting it down like this, it would go this way. And we can erase the initial one like that. We've reflected it about the x-axis. So there's the reference angle there, and it creates this angle in standard position all the way around. Okay, so completely around the circle is 360, and so then this red angle is going to be 360 minus the 40, 320 degrees. And finally, part C is saying what happens when we reflect this in the y-axis and then in the x-axis. Okay, so what would happen with that? Here's y, here's x. So we start off with a 40-degree angle, which would be here. We have an angle of 40 degrees and it's reflected in the y-axis, so it's going to be reflected this way first. Which puts the 40 degrees here. And then in the x-axis, then it's reflected this way. Which puts the 40 degrees here. Okay, so that's where it's being reflected to, and now we can erase our starting things. Okay, and so what is the angle in standard position now? So the angle in standard position is from the positive x-axis all the way to the terminal arm. Whew. That doesn't look very good. Okay, so notice that would be 180 degrees plus 40. So the theta is 180 plus 40, 220 degrees. Right, because it's 180 from the positive x-axis to the negative x-axis, and then plus the extra 40. Okay. All right, so there you go, everyone. That is Trig Lesson 4 for Pre-Calculus 11. The homework is from the Pre-Calc 11 textbook, which is on my website under the online learning folder. All right, and so, yes, if you want to read those pages, that will enhance the notes, and try page 83, numbers 2 to 8 all. You can check your answers in back of book. Check your answers in back of book. I'll also do a video showing the solutions to those and send them to you later in the week. All right, there you go, everyone. I will talk to you again soon.